This is the start of related rates. Related rates is generally considered a very difficult topic for my students. So I would just say take it slow through the video, take good notes, and text me or email with any questions. Calculus is the study of change, and more explicitly, it's the study of the rate of change, the slope, the average rate of change of one variable with respect to another variable. So in the problems that we're going to look at in this section, we are going to look at relationships that go on in the real world and look at some rates, and we're going to be solving for another rate. So we're going to be looking at rate of change. Because we are talking about the real world, a lot of things as far as one of our variables is time. That is a pretty common variable to use. So be ready to look at time as one of the dependent variables. Our overall goal is to find a relationship or a formula between them, and then we are going to find derivatives. In physics, we look at rates and the relationship between velocity, position, velocity, and acceleration. The derivative of position is velocity, and the derivative of velocity is acceleration. I'm not going to go over this problem, but this is an example problem in physics where you're given the position of a particle and you're asked to find different values and positions and velocity and acceleration. Here are other examples of the use of derivatives or rates of change in physics, chemistry, biology, and economics. A phrase often heard in a math classroom is that we never use math. When are we ever going to use this? Well, rates of change occur in all the scientists. A geologist is interested in knowing the rate at which an untreated body of molten rocks cool by conduction of heat. An engineer, an urban geographer, or meteorologist. There are so many examples of the real world of the use of calculus, and in particular rates of change. Here are more examples and talking about a single idea and that there are many, many interpretations. So the very idea of a derivative or a rate of change or a slope has so many interpretations depending upon what field of study you're involved in. In related rates, you're literally finding a relationship, hence the related part. You're finding a relationship between the variables and you're finding the derivative of all the variables, hence the rate of change. Why would we do this? Well, sometimes in the real world, it's easier to measure one quantity versus the other. For instance, it's easier to measure directly the rate of increase of the volume than the rate of increase of the radius, just as one example. Now, when we do this, we're going to have to look again at the chain rule to differentiate both sides with respect to t. So in the past, we have differentiated with respect to x, but now we're going to take the derivative with respect to time. So we're going to have to use the chain rule again and implicit differentiation. Everyone likes to have quote-unquote steps. I'm not really a step believer, but I know that students sometimes like steps. So here are some for you for related rate problems. First, I always try to draw a picture, if possible, of the situation. It just helps me to kind of get a grasp of what's going on in the situation. The next, you have to see your derivatives. What did they give you? What are you trying to find? What is your unknown? Next, find a relationship between the variables in your picture. And you're given an unknown, help you with that sometimes as a clue. And also, next, take the derivative with respect to time most often. Not always will you find the derivative with respect to time, but a lot of times you will. Now, when you're taking the derivative with respect to time, over here, don't forget about the chain rule. For instance, if you're going to take the derivative with respect to time of a variable that is an x, you first take the derivative with respect to x, and then you multiply by the derivative of x with respect to time. And if you're going to take the derivative with respect to time of a y variable term, you first take the derivative with respect to y, and then you find the derivative of y with respect to t. So that's for a y variable and an x variable. So Can you have a z variable? Absolutely. Can you have an a, an r, a h? Yes, you're going to have all kinds of variables. So you need to make sure that you understand your derivatives and you know how to use the chain rule to find the derivative with respect to time. Okay, in this example, you have a ladder. It's 10 feet long and it rests against a vertical wall. The bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. And so that's going to be important. And then it says how fast, if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So first, we have our picture. I already gave you that. So let's state what is given to us and what we need to find, our unknown. Our given and our unknown. So we're given what? Let's put some variables in there. Let's say this distance is x, this distance is y, and that's just this distance right here. The wall is taller, this is y. So we know that the rate that the ladder is sliding out from the wall is 1 foot per second. So that would be dx dt. It's 1 foot per second. So it's the rate at which x is changing. What are we trying to find? How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So we're trying to find this rate right here. So we're trying to find dy dt when x is 6 feet away from the wall. Okay, so we have our given and our unknown. Now we need to find the relationship. We have our given, our unknown, now our relationship. Well, if you look at this, it looks to me like we have a right triangle right here. You'll see that 90-degree angle. So the relationship is x squared plus y squared equals 10 squared, or x squared plus y squared is 100. Okay, so if you remember the steps, we first draw our picture, we have our given and our unknown, we have our relationship. Now we need to take the derivative with respect to time. So we are going to find the derivative with respect to time of x squared plus y squared, and that equals the derivative with respect to time of 100. So the derivative with respect to time of x squared would be 2x dx dt. Okay, so remember the chain rule. The derivative with respect to time, first take the derivative with respect to x, you multiply by derivative of x with respect to t. So this is the chain rule. Pretty important. Plus, derivative of y squared is 2y dy dt. And that equals the derivative with respect to time of 100 is 0. Okay, now we have a little thing. We need to plug in our values. So we have 2 times x, which is 6, dx dt, which is 1, plus 2 times y, dy dt equals 0. What is y? So I'm going to go back over here on my picture and look at more of my relationship. When x is 6, the ladder's 10, I need to find y. So again, it's a right triangle relationship. So I have 6 squared plus y squared equals 10 squared, dot, dot, dot. When I solve for y, I get y equals 8. So I'm going to put that over here. So now I have 12 plus 16 dy dt equals 0. So 16 dy dt equals negative 12. Dy dt, when I divide by 16, is negative 12 divided by 16. If I simplify that, that is what? Divide by 4, negative 3/4. And this units for feet per second. And that is my final answer. That is what they're asking me to find. So let's look back at what we did. We first drew a picture. Then we stated our given and our unknown. We had a relationship between the variables in our picture. We found the derivative with respect to time, so implicit differentiation. Then we plugged in what we knew and we solved for what we did not know. And that is the final step. Okay, for this one we have a water tank that has the shape of an inverted circular cone. I got a picture there with a base radius 2 meters and a height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so this is important. This is important. So let's start. We already have the picture. Let's start with the given. What are we given for this problem? Well, we're given that the water is being pumped into the tank. So if water is being pumped into the tank, so water's going into the tank, what is that changing? Well, that is the volume. So that's the rate at which the volume is changing with respect to time. And that is 2 meters cubed per minute. What do they want us to find? They want us to find the rate at which the water level is rising. So if water is being pumped into this tank, here's the water level, okay, and here's the height of the water level, right here. So they want us to find the rate at which the water level, so dH dt, when the height is 3 meters. Okay, so over here I have another smaller triangle, and this represents the water height. And the water height here is R. So we have R, which is this radius. Okay, and then we have H, which is the height of the water, and it's a right triangle. And then we also have the larger right triangle right here with 2 meters and 4 meters. Okay, now we need to find the relationship. What is the relationship? Well, we're finding volume and height. So the volume of a right circular or inverted circular cone with a base radius, that formula is volume equals pi over 3 r squared h. Now, at this point, you would usually take the derivative with respect to time, but we have a little problem here. Look at our relationship. It has two variables. When we take the derivative, we're going to end up with a dv dt, a dr dt, and a dh dt. Because we have two variables multiplied together, we'd have to do the product rule, and within the product rule, do the chain rule, and we would have a little bit of a problem there. The only problem is we don't know dr dt. We don't know the rate at which the radius is changing. All we know is the rate at which the height is changing. Well, actually, that's what we have to find, right? So is there another relationship to where we can find the radius in terms of the height, or vice versa? And it turns out we can if we look at similar triangles. So if we go over here, down here, looking at this green triangle up here, okay, this one, I'm outlining yellow. Look at that green triangle. And this baby triangle down here, these are called similar triangles. So using similar triangles, we can say okay, so using similar triangles, we know that 4 is to 2, height is to the radius, as h is to r. And if we solve this, we get 4r equals 2h, and we get the radius is h over 2. So we're going to put that over here. So volume is pi over 3 r h over 2 squared h. And we simplify that, we'll get the volume is pi over 12, because 2 squared is 4 times 3 is 12, h cubed. Okay, now we're going to take the derivative with respect to time of the left side. Now will equal the derivative with respect to time of the right side. Okay, so the derivative with respect to time of v is 1 dv dt equals pi over 12 is a constant, so we're going to bring it out. And the derivative of h cubed is 3h squared dh dt. Okay, now we can fill in what we know. What do we know? We know that dv dt, we know that dv dt is 2. So 2 equals pi over 12 times 3. Find dh dt when h is 3 squared dh dt. So we get 2 equals 27 pi over 12 dh dt. So multiply by 12, we get 24 over 27 pi equals dh dt. And if we simplify that, we get 8 over 9 pi, and this is meters per minute, and that is dh dt. And that is our final answer here. All right. Okay, so let's go back. We first found our given, our unknown, we found our relationship, and we didn't want to take the derivative with respect to time of our relationship because we would have had a dr dt, and we don't know the rate at which the radius is increasing. And hopefully you look at the picture and you can see that the radius is going to get higher or more as the water fills. So we don't know that rate, so we found another relationship of r in terms of h and put that in before we found our derivative. Okay, on this one we have a plane flying horizontally at an altitude of 1 mile, and then we have it's at a speed of 500 miles per hour, which is pretty important, so I'm going to do that, circle that. It passes directly over the radar station, which is down here. Okay. It says find the rate at which the distance from the plane to the station, which is this y distance down here. Find the distance or find the rate at which that is increasing when it is 2 miles away from the station. So first, let's state what we're given. We're given that it is 1 mile up. We also given the speed is 500 miles per hour. So this rate right here, dx dt, is 500 miles per hour. What do they want us to find? What is our unknown? Let's read. It says, find the rate at which the distance from the plane to the station, so that's this rate, find dy dt, how fast that one is going, when it is 2 miles away from the station. So is that x equals 2 miles or y? Well, when the airplane is 2 miles away would be y. So when y equals 2 miles. Okay. So what is our relationship? Well, again, we have a nice relationship. It's just the Pythagorean theorem, which says x squared plus 1 squared equals the hypotenuse squared. Okay, so now we need to find the derivative with respect to time of both sides of our equation. Okay, the derivative with respect to time of x squared is 2x dx dt. Derivative of 1 is 0. And the derivative with respect to time of y squared is 2y dy dt. So I can eliminate the 2 from each side. So I get x dx dt equals y dy dt. Okay, so we know what dx dt is. It's 500. I don't know what x is. This is 500 miles per hour. I know y is 2, and I have to solve for dy dt. So I need to figure out x when y is 2. So I've conveniently drawn another right triangle, and I need to know x, and I know y is 2, and I know this side is 1. So I know x squared plus 1 squared equals 2 squared. X squared plus 1 equals 4. So x equals the square root of 3. So square root of 3 here. So then I can go over here and I get 500 square roots of 3 equals 2 dy dt. So to find dy dt, divide by 2. So 500 square roots of 3 divided by 2. So 250 square roots of 3 miles per hour is dy dt. And I could put that in my calculator and figure out how much it is if I wanted to know in decimal form. There you go. Okay, this one says water pours into a fish tank. So again, we have water coming into something at a rate of 0.3 cubic meters per minute. So cubic meters per minute. So it's a big fish tank. So water's going in here, down in here. So this is important. And if water is being poured into it at a rate, this is a rate of volume. Okay, so then it says, how fast is the water level rising if the base of the tank is a rectangle of dimensions 2 meters by 3 meters? So this is 2 meters by 3 meters. Let me draw this down here. It's a rectangle. Okay. And this is 2 meters by 3 meters, or vice versa, it doesn't really matter. And then it's slowly filling up. So there's the water level slowly rising over time. So water's being poured into it. Okay, so let's talk about what we know, what we are given. We are given that the rate of change of volume with respect to time, because that's the rate that the water is coming in, and that's going to change the volume of the tank, and it's 0.3 cubic meters per minute. What do they want us to find? What is our unknown? Our unknown says, how fast is the water level rising? Well, let's call this water level H. So how fast is dH dt rising if the tank is 2 meters by 3 meters? Okay, so we need a relationship. Obviously, this is going to be volume. Our volume of our tank is length times width times height. So our volume is 2 times 3 times h. And because we don't know how tall that water level is. Okay, and by the way, 3 is this length here, right here. I'm going to highlight it in red. That's what is 3. It's not the height of the water. And the height of the water is over here, h. Okay, that's the height of the water. So again, our volume is going to be 6h. So now we have our given, our unknown, our relationship, our pictures. So now we need to find the derivative. So the derivative with respect to time on the left and the derivative with respect to time on the right. So we get 1 dv dt equals 6, because the derivative of 6h is 6 dh dt. Now we fill it in. dv dt is 0.3. So we have 0.3 equals 6 dH dt. So 0.3 divided by 6 equals dH dt. Okay, let's see what that is. And what would our units be? So it's 0.05, and this would be, what are our units? Meters per minute is how fast the height in that tank is changing. So for every minute that water is going into the tank at a rate of 0.3 cubic meters per minute, the height is changing at the rate of 0.05 meters per minute. Okay, this one is an actual problem from your homework. So I'm not going to finish it, but I'm going to give you some hints on it. So it says a tanker that ran aground is leaking oil that forms a circular slick about 0.2 or a fifth of a foot thick. To estimate the rate, dV/dt, in cubic feet per minute at which oil is leaking from the tank, it was found that the radius of the slick was increasing at 0.43 feet per minute when the radius was 600 feet. Find dV/dt using pi. Okay, so we need to find dV/dt when r is 600 feet. So the rate at which the volume is changing when the radius of the leaking oil is 600 feet. Okay, note these formulas that they gave us. Okay, so if I take A equals pi r squared, I can put in my radius of 600 and find A and plug that in over here for A, but the only problem is then I won't have a variable to take a derivative with. So I'm going to take both of those and take the derivative of them with respect to time. So on this side, I get 1 dV dt equals 0.2 dA dt. Now this is what I'm trying to solve for, right? This. So if I just knew dA dt, I would be good. But they haven't given me dA dt. They did give me over here, they gave me dr dt. So let's look back and see what we can do. So over here on the left side, we get 1 dA dt, that's what I need, equals the derivative. Okay, so we have pi r squared. Pi is a constant. The derivative of r squared is 2r dr dt. Okay, so we get dA dt equals 2 pi times r. Well, what is r? The radius is 600 feet times 600 times dr dt, which they gave us is 0.43. So I'm not going to finish this, but once you know dA dt, you can then sub that over here for dA dt and solve for dV dt for your homework. For this situation, you have a still pond and somebody has thrown a rock into it and it creates a circular ripple. And whenever students look at problems like these, most of the time they're okay, but they're not sure what the rate. So here's a key word. See this word increasing? That is a rate. If it says it increased, that's a distance. But when it says it's increasing, that's a rate. So now I'm going to put the unknown, the given, and the relationship. Okay, for this one, for a hint, this is your exit ticket. For a hint, you are going to be looking at Pythagorean theorem. Other key things are 1/2 hour later. So if one car is going 50 miles per hour at its rate, how many miles has it traveled in half an hour? And if this one is going 60 miles per hour, how many miles did it travel after half an hour? That will help you to figure out your unknown. And knowing those two rates will help you with your given. And you should get to the answer of D. So that can help you check your work. And you will upload that to Blackboard.